So the next concept or the next operation we'll learn on a matrix is called the transpose of a matrix. Right? Suppose if A is a matrix, the transpose of A is often written as A with a capital T on top, or some books may also write it as A small t. Right? Some books you may also see this A TR sometimes written. Okay, so this means transpose of a matrix. I'll explain you what the transpose of the matrix. First, let's learn the notation here. So it can be written, or in some books you also see A dash written to represent the transpose of a matrix. And the concept of transpose of a matrix is a very simple concept. Let's take a simple example. Imagine I have a matrix like this, right? Imagine I have a matrix like this. Okay, let's say this matrix is A. Okay, let's assume this matrix is A. So the remember what is the order of this matrix? It has 2 rows, right? And it has 3 columns. It has 2 rows and it has 3 columns, right? So the transpose of this matrix is nothing but you basically take each row, take your first row and write it as the first column. Okay, so make your rows of the original matrix as the columns of the second matrix. So now if this matrix is A transpose, right? What are we doing here? We are taking this first row here and writing it as a first column. We are taking the second row and we'll write it as the second column, right? So a matrix which is of size 2 cross 3 would become a matrix of size 3 rows and 2 columns, right? So in a nutshell, if you have a matrix A which is of size m cross n, the transpose of this matrix now would be of size n cross m, because you're literally converting each of these rows into a column, right? Or in other words, look at this. There is another way to write. So suppose look at this, right? Look at this cell or this value. This is in first row and second column, right? This is in first row and second column, right? So now we can write this. So we write this often as Aij, or we can also write it as A12 with I equals to 1 and j equals to 2. So if you want to refer to this cell, because this cell is in the first row and the second column, we often write it as A12. Okay, A12 basically means the value of the cell that is in the first row and second column of the matrix, right? So what A transpose does is, if you have a matrix, every value Aij in this matrix, right? If you have a value Aij in this matrix, right, where I is less than equal to m and j is less than equal to n, right? So that's what it is, right? So Aij, so the Aij cell, look at this. This is A12 here, right? In this matrix, this is A12, right? A12 equals to 2. What happened to 2 in this? In this matrix, this became second row and first column, right? So Aij in the original matrix would become A transpose Ji. Look at this. This is Ij and this is Ji. Okay, this is another way to define what the matrix, what the transpose of a matrix is. Okay, very simple. It's a very, very simple operation, right? You simply convert each of these rows into columns. That's all there is. Okay, so there are a few important properties. There are a few important and simple properties of transpose operation. Let me go over each of them. Then we'll see an application of this concept called transpose, right? See, remember, this is a very simple operation. This is taking an m cross n matrix and converting it into an n cross m matrix by just writing each of the rows as columns of the new matrix. That's all there is. Okay, again, this operation is something that we'll keep using throughout our linear algebra course. All right. So now the first thing here is, the first property here is A transpose. The transpose of A transpose is A itself, because look at this. I have the matrix, original matrix A. I've changed the rows to columns, and then I obtained A transpose. Now if I again change the rows to columns, I'll obtain A back, right? So this is a very simple property of a transpose of a matrix. Similarly, if you have two matrices A and B, A plus B transpose, right, is equal to A transpose plus B transpose. Again, all of these properties you can verify them manually. Okay, you can construct matrices, right? You can construct matrices with A11, A12, A21, A22. Construct any matrix and you can verify that these properties are true using simple algebra, right? It's not very fancy at all. The most important property of transpose, right, which is slightly tricky, is if you have A into B, the transpose of the product of two matrices A and B, this is not A transpose into B transpose. This is actually B transpose into A transpose. This is very, very important. Okay. So again, you can verify this. We can verify this rigorously and prove it rigorously. One way to think about it is this. Look at your A matrix. Let's say A is n cross m. For B to be for us to be able to multiply B with A, B has to be m cross something, right? Let's look at the transpose of this. What will the transpose of this? The product of both of them. Look at this. The product of both of them. Let's call it as C. What would be the dimensions of C? Dimensions of C would be n into k. Would be n into k. Transpose, which means the whole resultant matrix. Okay, let's call that matrix D will be k into n. Okay, now this is not B A transpose B transpose. Okay, this is B transpose A transpose, because again we can just argue. Again, I'm not proving it rigorously here, but I'm just trying to give you some intuition on it based on the order of the matrix itself, based on the size of the matrix. This is called the order or the size of the matrix, right? Now if you take B, what is the dimensions of B transpose? Let's look at it. B transpose is k cross m. Okay, what about A transpose? Look at this. A matrix is of size n cross m. So A transpose will be m cross n. So when I multiply both of them, I would see, because m and m is matching here, I would get a matrix which is k cross n. Of course, you need to prove that rigorously. See, I'm just matching the dimensions of the matrix or the size of the matrix here. On the other hand, if AB transpose was A transpose B transpose, everything would fail. Because what are the dimensions of A transpose? A transpose dimensions are m cross n. What are the dimensions of B transpose, or what is the order of B transpose? It is k cross m. Now you can't multiply both of them. It's not possible to multiply both of them if n is not same as k. So AB transpose, we know, results in a final matrix which is of size k cross n, and it is not equal to A transpose into B transpose, because A transpose and B transpose may not be multiplicable. You may not be able to multiply them in the first place. Okay, so the simplest way to remember this is, it cannot be A transpose B transpose because you can't multiply these two matrices, but you can multiply these two matrices, so you can prove rigorously. Again, I'm not doing the proof rigorously, but I'm just giving you an intuition on why it is not A transpose B transpose and why it could be B transpose A transpose. There is still more proof left here. Similarly, there is another very interesting property, which is, if you have a constant C, right? Constant C multiplied by matrix A transpose is same as C into A transpose. Remember that C is a constant. Okay, C is a scalar, right? So this is basically multiplying a matrix with a scalar. If I take the transpose of that, this is equal to this. Again, this is also extremely simple to prove. There are many other properties of transpose that we will learn slowly as we learn more and more concepts as we go forward, right? But just like the way a vector, so just like the way a matrix has a transpose, a vector also can have a transpose. Let's look at it. A vector also can have a transpose. A vector can also have a transpose, right? Let me show that to you. Till now, whenever we talked about, let's assume we are talking about a two-dimensional vector. Okay, let's assume I have a vector A, which is a two-dimensional vector. I'm representing it as a vector like this, wherein I have the x coordinate here and the y coordinate here. If you think about it, right? Or let's actually, instead of writing x and y here, let's actually write it as A1 and A2. Okay, so if you think about this vector in terms of a matrix, right? This matrix has two rows and only one column, right? So if you want to think about the order of this has two rows and one column. That's what, right? That's what is this vector A. Now what is A transpose now? Okay, again, I'll just write it as A transpose, okay, without putting this, or let's put the arrow here, just to make sure that you understand that A is a vector. If A is a 2 cross 1 vector, right, what will A transpose be? A transpose will look like this. Because what happens? I took a column, I made it like a row. So now this has only one row but two columns. Okay, so this is often referred to as a column vector. This is often referred to in linear algebra as a column vector. So anytime you say that A is a vector, you inherently represent it as a column vector, because all the components of that vector, you put them in a single column. Because look at this. Look at the number of columns here. The number of columns is 1. So whenever somebody says A is a vector, the default, what they mean, by default, they mean it's a column vector, or you can, this is also sometimes called as a column matrix, by the way. This is also sometimes referred to as a column matrix, right? Now, what is this? Now, in this case, I have only one row. So this is called as the row vector. This is referred to as the row vector or the row matrix, right? Now, okay, so if you have a vector A, which is a column vector, you can transpose that vector by making the column into a row and obtain a row vector or a row matrix, which has only one row but multiple columns. All this is good. So we have learned about vector transpose. Now, why is this important? There is a very important concept called as, dot product. Sorry, I mixed up terms there. Okay. So there is a very interesting concept called as a dot product between two vectors. Very interesting and a very, very powerful concept. Okay, let me just explain this concept in 2D, but this concept is general enough that you can use this concept in any dimensional space. So I have two dimensions here, x and y, right? I have a vector here. Let's call this vector as A. Okay, so let's assume I also have an other vector. Okay, let's assume I also have an other vector B. Okay, so I have these two vectors A and B now. So that there is an operation that you can perform on these two vectors called the dot product, which is often written as A dot B. Okay, so this is one type of product, or one way of multiplying two vectors. There are other ways of multiplying two vectors. Okay, so this is called the dot product. Okay, so here I'm skipping drawing these arrows because that is implicitly clear that A and B are vectors. Okay, so A and B is defined as, for example, now let's say A is equal to, so now let's assume A is equal to A1, A2, B is equal to B1, B2. Let's learn the numerical part of it. The dot product between A and B, is written as A transpose multiplied by B. Okay, first let's learn the numerical aspect. I'll also tell you the geometrical interpretation of dot product in a while. Okay, so what does this mean? Look at this. What is A? A is a column vector by default unless otherwise stated. B is also a column vector. The moment I say A transpose, now what happens now? A transpose is a row vector, right? A transpose is going to be like this. This is going to have one row and two columns. What about B? B has B1 and B2. This has two rows and one column. If I multiply these two using the matrix multiplication approach, look at this. If I multiply both of them, because this is 2 and this is 2, they both are I can multiply both of them. When I multiply both of them, the result that I get is a 1 cross 1 matrix, right? Or I can think of it like a scalar, because there is only one value there, right? And what will that value be? A1 multiplied by B1 plus A2 multiplied by B2. See, look at this. I'm taking this row. We have seen matrix multiplication, right? This is the same concept. A1 multiplied by B1 plus A2 multiplied by B2. So the dot product of two matrices, the dot product of two vectors, not matrices, sorry. So the dot product of two vectors A and B is basically component wise you multiply. You're multiplying component wise and you're summing up the whole thing. And this will finally result in a 1 cross 1 value or simply a scalar. Okay, so, or this is simply a scalar, right? So this is what numerically A dot B or dot product between A and B means. In some books you'll also see this notation of A comma B to represent. This is also one way that some mathematicians and physicists write to represent the dot product between two vectors. In some books you'll see this notation. They all are the same. In a nutshell, the dot product between two vectors is component wise multiplication followed by addition. That's what it is. But what does it mean geometrically? Right? We have understood it. So what does it mean geometrically or intuitively? What does it mean? Okay, so we have seen it what it means numerically, but let's see what it means geometrically. Okay, so let me redraw this. Okay, I'm not drawing the axes here. So let's assume this is my vector A, right? Let's assume this is my vector A and this is my vector B. Okay, this is my vector. I'm again skipping drawing these arrow marks. If if this is A and this is B, see, this is one way of thinking about a dot product. There is another way. So this is the numerical way of thinking about a dot product. There is a geometric way of thinking about a dot product. If these two are two vectors, there is an angle between both of them. Let's say that angle between these two vectors is theta. Remember, these two vectors could be 2D vectors or 3D vectors or 4D vectors or 1000D vectors. Doesn't matter, right? If these are two vectors, there is an angle between both of them. An alternative definition of dot product is A dot B is equal to, right? A dot B is equal to the length of vector A multiplied by the length of vector B. See, look at this. This is the length of A, right? This is the length of B, right? Multiplied by the cos of theta, which is the angle between these two vectors, right? So imagine if somebody gives you two vectors. Let's say A is like this, B is like this, and you want to compute the angle between both of them, because these two are going to be same. Look at this. These two are going to be same, right? Or in other words, imagine that A and B are two-dimensional vectors. This is same as the length of vector A, the length of vector B, and cos theta. And we know the length of vector A from Pythagoras theorem is a1 square plus a2 square under root, right? We know the length of vector B is b1 square plus b2 square whole under root and cos theta. So if you actually give me two vectors, if you give me actual values for a1, a2, b1, b2, some numerical values between all of them, I can compute theta, right? Then I have a1, b1, a2, b2. I'll just place these values here, and if I just divide a1, b1 plus a2, b2 divided by these two square roots, right? Square root of a1 square plus a2 square multiplied by square root of b1 square plus b2 square. This is equal to the cos of the angle between them. So if I know a1, a2, b1, b2 numerical values, I can compute this expression. When I compute this expression, I can take the cos inverse of it to obtain the angle between them, right? So the dot product also helps us obtain the angle between two vectors, which is extremely important. Okay, again, this is one of the concepts that I've used extensively in machine learning and artificial intelligence. Okay, this is one of the most foundational concepts. The dot product is one of the most foundational concepts that I've learned, which I've used extensively in my career in both machine learning and artificial intelligence on a day-to-day basis. Okay, of course, I cannot go into how it is used without going into the depth of machine learning and AI, but just take my word for it that it is used extensively. Okay. Similarly, there is another way of thinking about this whole thing, which is called, so let's assume I have a vector A here, right? And let's say this is my vector B. Okay, this is my vector B. Now, let's assume this angle is theta. Okay, there is a concept called as projection. Okay, there is a concept called as projection. Okay, the concept of projection works like this. Okay, so the concept says, so if I take this vector, if I draw a perpendicular line here, remember that this line is perpendicular. This line is perpendicular to B. If I draw this line, right, I get this length. Now, what is this length if you think about it? What is going to be this length? Imagine, so I have this vector A and vector B. This could be in 2D, 3D, 10D, 100D, doesn't matter. If I draw a perpendicular line here, right? If you know basics of trigonometry, so what is this? What is this going to be? If this length is A, let's assume this length is A. Okay, so this length is A. Okay. Now what is going to be this length? This length is going to be A cos theta. Right? This length is going to be A cos theta. Right? And this is said to be, so if you create a new vector, if you create a new vector like this, if you create a new vector in the direction of vector B, which is of length A cos theta, this is said to be the projection. This is said to be the projection of vector A. This is said to be a projection of vector A onto B. So what is projection of vector A onto B? It is nothing but it's a new vector of length of A cos theta, right? This is the magnitude of this vector. Okay, this is the length of this vector. And what is, so this is the length of the new vector, right? And what is the direction of the new vector? The direction of the new vector is same as vector B, is same as your vector B. Okay. So projection is also an important concept, because now look at this. Now look at this. I can write my dot product. I can write my dot product A dot B. Okay. What is A dot B? A dot B is nothing but A into B cos theta. Now I know that A cos theta, I can write A cos theta as projection of vector A onto vector B. So this is how it is often written as. Some books write it as projection AB, some books write it as projection BA. Both of them are okay. So here in this video, we'll write it as projection of vector A onto vector B. Okay, so I can write this as length of vector B. I can write the dot product also as length of vector B multiplied by projection of vector A onto vector B. Okay, so this is another way to define dot product. Okay, so we have seen three ways of defining it. One is the numerical way. If you give me the coordinates of these two vectors, I can define the dot product. We've also seen a different way of representing the dot product geometrically by using the angle between them. We can also write the dot product using the projection of one vector onto the other vector. Okay, so this concept of projection is a very and the whole concept of dot product itself between two vectors is a superb concept which is used every day, right? In lot of applied mathematics, computer science, especially artificial intelligence, machine learning, advanced statistics, all of them, they use it every day. Okay. Similarly, here remember, we are using the concept of transpose itself that we just learned at the very beginning of this video, right? That's why I'm trying to connect the concept of transpose and dot product, because we are using the operation of a transpose of a vector here, right? When we arrive at the formula for dot product. Geometrically, this is what dot product means, and this is another way of thinking about a dot product using the projections.